Okay, so we're very happy to have today with us Dr. Katzelnick, and he's going to talk about an extension of Grothendieck's inequality and correlation clustering.
Okay, so thanks, Well. Everyone can hear me?
Yeah.
Okay. So what we're going to talk today is about a problem of correlation clustering. And the title of this talk will be Maximizing the Correlation, Extending Grothendieck's Inequality to Large Domains. Okay, so I'm going to start with the model of correlation clustering. And in this model, we are given a graph, an undirected graph, where the edges are labeled by a plus or a minus sign. A plus sign indicates that the two nodes are similar, and a minus sign indicates that the two nodes are dissimilar. And we are also given a weight function on the edges. And what is the goal? What is our goal in this problem? Basically, we want to find a clustering of the graph, that is a partition of the nodes in the graph, in a way that agrees the most with the labels of the edges. So plus edges should reside within cluster because we want similar nodes to be together in the same cluster, and minus edges should cross between cluster because we want dissimilar nodes to be in different clusters. Okay, so let's see an example. So we can consider this this graph. Here we have some nodes and we have some edges with a plus sign and some are with a minus sign. And you can consider this this clustering. Here we have 4 clusters, and some of the edges, some of the plus edges are within cluster, some cross between cluster, and so are the minus edges. Some are inside cluster, and so some of them cross between clusters. Okay, so the first important thing to notice is that a perfect clustering does not always exist. For example, if you look at this this triangle, these 3 nodes, then you can see that we have 2 plus edges and 1 minus edge. So basically, this means that these 2 nodes have to be together in the same cluster, and so these 2 nodes have to be together. But here we have a minus edge. So basically, this means that in every clustering, one of these edges will not be satisfied. Okay, so if we want to measure how good a clustering can be, then we can look at the agreements. What are the agreements? The agreements are the edges that are classified correctly. For example, these are the plus edges that are within clusters and the minus edges that cross between clusters. So we can try to maximize this number, try to maximize the number of agreements. Another way to measure how good the clustering can be is to look at the disagreements, which are basically the edges that are classified incorrectly. So these are the edges that cross between clusters, for example, like this plus edge, or the minus edge that are within clusters. Okay, so this is the model. And now with the agreements and the disagreements, we can define the following objectives. Okay, so the first objective is called max agree. And it's very basic. We just want to find a clustering that maximizes the number of agreements. These are the edges that are classified correctly. And the second objective is called mean disagree. And here the goal is to find a clustering that minimizes the number of disagreements, right? We want to have the least number of disagreements in the clustering. And the third objective is called max score. And here we want to maximize the correlation. And what is the correlation? The correlation of a clustering is just the difference between the number of agreements and the number of disagreements. So you take all the agreements in the cluster and you subtract the number of disagreements, and what you get is the correlation. So intuitively, you can think about it like you're trying to simultaneously maximize the number of agreements and minimize the number of disagreements.
But since the number of edges is the same, then aren't all these like the same?
No, they're not the same. So they look very similar. I mean, okay, every edge that is not agreement is a disagreement. So you can try to look at the complements of the agreements, which are the disagreement, but actually these are not the same objective. They have a different hardness.
So Eddie, you had a question?
Yes. So like the goal is actually to find a clustering with as many positive edges, but I don't care how many minus edges I have. Is that correct?
Okay, so again, in the max degree objective, the goal is to find a clustering with as many agreements. Agreement is a plus edge that is within a cluster and a minus edge that crosses between clusters. This is an agreement.
So in other words, I don't care how many disagreements I have in a cluster, as long as I'm maximizing the agreement.
Yes, this is in the max agreement, max degree objective. In the min disagree objective, you want to minimize the number of disagreements, so you don't care for the agreements. But in the max score objective, you care both for the agreements and for the disagreements. So every edge is taken into account. Okay, so it's a good, these are good questions. Okay, so now when we have this objective, let's talk about some motivation for this model. So on the theory side, you can see that this model captures some very basic graph problems. For example, the mean disagree objective captures this problem, mean ST-cut and multi-way cut and multi-cut. So very simple reduction between this problem. And also if you take the max agree objective, and if you limit the number of clusters to be at most 2, it will capture the max cut objective, right? Because here you want to find a cut, so a cut with the maximal value, so you can consider a graph with only minus edges. And if you find a clustering to 2 clusters, then this will be exactly max cut. Okay, so on the practical side, we also have some interesting applications like image segmentation and cross-lingual link detection, and so on. Okay, so let's talk about some previous work in this model. So there's actually quite a lot of work, and here I'm going to present just some of the most relevant work. So here I have some approximation algorithms for this problem. And for example, for max agree, if you're given a general graph, it's very easy to find a half approximation. There's a very simple combinatorial algorithm. And you can even get a 3/4 or 3/4 plus some small constant approximation for max agree and general graph. And this will, here you'll need to use some semi-definite relaxation and some rounding technique that is similar to max cut. And we also have some pitas for complete unweighted graphs and bipartite graphs. And we also have algorithms when we are restricting the number of clusters in the output. Okay. And for the mean disagree objective, we have an order of log n approximation for general graphs. And this is, there we use some metric methods and some region growing techniques. And we also have some constant factor approximation when the graph is complete and unweighted, and also for bipartite graphs. And for the max score objective, which is somehow the hardest objective of these 3 objectives, we know an omega of 1/log n approximation for general graphs. And we're going to talk about this approximation in a few slides. And the rest is unknown. So this is the objective that we're going to talk about today. Okay. If you have any questions, feel free to stop me anytime. So what did we do in our work? We studied the problem of max score. Again, this is the 3rd objective. on bipartite graphs. And we also extended it to the problem of max k-core. And this is the problem of max core, but we are limiting the number of clusters in the output to be at most k. For example, in max 2 core, we want to solve max core, but we want to have only 2 clusters in the output. And then we present some approximation algorithms for this problem. And we also show how they relate to Grothendieck's inequality. And we also show how they can extend it to larger domains.
Dol, can I interrupt for a second?
Yeah, sure.
Can you repeat for those who were in the other room first?
Sorry, there was a misunderstanding.
Pardon?
No, sorry, there was a little misunderstanding with the...
Yeah, so what is the max core objective function?
Okay, so the max core objective function is want to maximize the correlation, and the correlation is basically the difference between the number of agreements in a clustering and the number of disagreements. So you get every agreement and you pay for every disagreement.
Okay, good.
Just one more question. You showed that the log n approximation for max core. Is it tight?
This is a good question. I think so. I think that this is tight. There is a similar hardness. Okay, so let's continue. So this is what we did in our work. We studied the problem of max core on bipartite graph, and we extended it to max k core. So what was the previous work on max core? So there is a work of Charikar and Wirth from 2004, and they studied the problem of maximizing a quadratic form, and we call this problem max quad. What is this problem? We're given a matrix, an n by n dimensional matrix, and we want to find an n-dimensional vector over plus and minus 1 that will maximize this form, x transpose bx. And it's very easy to notice that if you want to solve max 2 core, that is, you're given a graph and you want to find a clustering with only 2 clusters, then this is exactly like maximizing a quadratic form. Because if you have, if you solve this problem, right, you have a vectors of plus and minus 1, and you put all the nodes that get 1 in one cluster and all the nodes that get minus 1. You put them in the other cluster, and you got 2 clusters, and the value of this solution is exactly like the value of this form.
So this means that your edges are weighted?
Yes, the edges in the graph can be weighted. Okay, and what they presented is an omega of 1 over log n approximation for this problem for max quad. And this algorithm used some semi-definite relaxation and random projections. And then they showed how you can use this algorithm to solve max core, not just the restricted problem when we have only 2 clusters. So basically, they showed a reduction from max core. And let's see the reduction. So you are given a graph, again, with sign and weighted edges, and you define the following metrics. You say that Bij will be equal to the weight of the edge ij if it is a plus edge, or just the negative weight, the minus of the weight, if this is a minus edge. And then you solve this problem, the max quad problem, and you get a solution, and you define this clustering that is induced by this solution. Again, you put all the nodes that get plus 1 in one cluster and all the nodes that get minus 1 in the other cluster, and this is the clustering. And then you define this clustering, which is the all singletons clustering. This is the clustering that every node is in its own cluster. And then you just return the best clustering out of these 2 possibilities, either S or T. Okay, so this is the reduction. It's a very simple algorithm. And they showed that if you have an alpha approximation for maximizing a quadratic form for max squad. If you solve this problem approximately with a guarantee of alpha, then you get an alpha over 2 plus alpha approximation for max core. So this whole reduction gives you an alpha over 2 plus alpha guarantee for max core. So if you take this omega of 1 over log n approximation for max squad, and you plug in here in this expression, you get an omega of 1 over log n approximation for max core. So this is a very nice reduction that gives you a nice approximation for the problem. Okay, so again, like Yaron asked me before, this is sort of tight, also for maximizing a quadratic form and for max core and general graphs. And now you can ask if we can do better for other types of graphs. And this is what we're going to see today. We're going to talk about bipartite graphs and bipartite forms. So we're going to define the following problem, which is called max biquad. And it's similar to max quad, but here we want to maximize a bipartite quadratic form. So we're given a matrix, but now it is an n by m dimensional matrix. And we want to find two vectors, x and y. X is an n-dimensional vector over plus and minus 1, and y is an m-dimensional vector over plus and minus 1. And these vectors will maximize this form, x transpose a y. Okay, so you may think that this problem is somehow harder than max squad. For example, if you plug in m equals n, then it may look like you get the max squad, but this is not true because here you want to find two vectors, x and y, and when you solve max squad, you want to find just one vector. And in fact, you can show a reduction between this problem that tells you that if you have a solution for max squad, you can also use it to solve this problem. Okay, and again, this problem is equivalent to max 2 core on bipartite graphs. If you think about it, you can take the partition of the graph into two sets. You take the one side of the graph, it will be the rows in the matrix. You take the other side of the second side of the graph, and it will be the columns in this matrix. You can show that these two problems are similar. Okay, and now we can ask how to solve this problem. So we have this problem of maximizing a bipartite quadratic form, and we want to somehow solve it, or we want to find an approximation algorithm for this problem. And this is, we typically achieve this algorithm with the natural semi-definite program. And before I'll show you what is the natural semi-definite for this problem, I'm going to talk about Grothendieck's inequality. Okay, so what is Grothendieck's inequality? It basically says the following thing. It says that there is a universal constant, kg, such that for every matrix A, the following holds. So the left side is this constant, kg, times this value. And let's try to understand what do we have here. So on the right-hand side, we have this, we want to find two vectors, x and y. X is an n-dimensional vector, and y is an m-dimensional vector, like before. And we want to maximize this this value. So this is exactly the bipartite form. This is exactly x transpose a y. So on the right-hand side, we have the max biquad objective. And what do we have on the left side? So we can see that instead of numbers xi and yj, we now have vectors. We have yi and vj. And we don't just look on the product of them, we look at the inner product between them. And in fact, these vectors are unit vectors in this n plus m dimensional hypersphere, or unit hypersphere. And we want to maximize this value. So in fact, what we have on the left-hand side is basically the natural semi-definite relaxation for max biquad. And this is what this inequality tells us. So there is a universal constant kg that is for every matrix A, the left-hand side is at most kg times this value. Okay, so you can see this, this statement, this inequality, it dates back to the 1950. So probably Grothendieck didn't really care for correlation clustering or max biquad or even approximation algorithm at all, because it was long before we even started to talk about P versus NP.
So can you tell us what it was originally intended for, in what context he developed this?
Yes, I think that he developed this in the context of functional analysis and maybe topology, but I'm not entirely familiar with these fields, but I think that this is the relation. Okay, I think that he was mainly interested in this constant in kg. So we wanted to know what is this constant. Okay, so what do we know about this constant? We know from Krivin's work that this constant is at most this number 1.782. And again, also Krivin, I think this work is from the 70s, and he also really didn't care for the algorithmic application for this inequality. He only wanted to calculate this constant. So he gave a proof that said that this constant is at most 1.782, but his proof was constructive. So we got an algorithm or an efficient algorithm for rounding this semi-definite relaxation. Okay, and Krivin, he also conjectured that this is the correct value, this constant, but I think 10 years ago, there was a work by Braverman et al., and they showed that this is not the right solution. So actually the real constant is slightly smaller than this value. Okay, and in the 90s, Reed showed that this constant is at least this number. So we have this lower bound. Okay, so we can see that we still don't know what is the second digit in this number. So we don't know if it is 1.7 something or 1.6 something. Okay, so let's see what we can do with this rounding algorithm for our problem, for max score. So we can try and take Krivin's algorithm. Actually, Krivin gave an algorithm of he showed that this constant is most 1.782, and this basically gives us an alpha approximation where alpha is roughly 0.561. So we can take this algorithm and plug it into the Charikar-Wirth reduction, and we just replace this part where we're trying to solve the max quad problem. We're replacing with the algorithm that solves max biquad. And we just use the same reduction. So if you do that and you plug it here, this 0.5611 approximation factor, then what you get is this approximation, 0.219 for max score on bipartite graphs.
So can I stop you for a minute? So there was a work some time ago showing that Krivin's one can be improved. So is this the same setting?
I'm sorry, I think there is a work that showed that Krivin's cream are optimal.
So this is Braverman, the Makarichuk brothers, and Safnal from 2011.
Yeah, this is the work that showed that that Krivin's constant is not the right constant. Okay. Yes, Braverman et al., 10 years ago. Okay, so we can take Krivin's algorithm, this 0.5611 approximation, and plug it into the reduction, and then we just get this very simple and straightforward approximation for max score on bipartite graphs. But you can see that if we, considering this lower bound on this constant, then basically this means that we cannot hope for a better approximation for max biquad that uses this relaxation that achieves an approximation better than 1 over this number, because this constant is basically the 1 over the integrality gap of this relaxation. So again, if you plug in 1 over 1.6769 in the alpha over 2 plus alpha expression, then what you get is a barrier of 0.2296. And basically this tells us that if you try to use this reduction and you want to solve the max biquad algorithm by rounding this natural semi-definite relaxation, then you cannot hope for a better approximation than this number. Okay, so we have this barrier that we cannot go beyond it with this technique. Okay, and another important thing to notice is that in this reduction, we might end up with a very large number of clusters. So it may output the all single solution. And if, for example, you want to find a clustering with constant number of clusters, then this will just not work. So we have to try something a little bit different. Okay, so before I tell you what to do, I'm going to show our results. And the first result is a polynomial time and 0.254 approximation algorithm for max score on bipartite graphs. So you can see that this number goes beyond the barrier of this technique. And the second result is basically that we can approximate the problem of max k-core on bipartite graphs with the following guarantees. And we can see that when k equals 2, then we get exactly the bound of Crevin's algorithm of 0.5611. And as k grows, we get a worse approximation factor. For arbitrary large k, we get the same approximation factor for max score, this is 0.254. Okay, and I want to talk a little bit how these two problems actually extend Grothendieck's inequality. And this, okay, so this is the original inequality. And you can see that if you look at these vectors, x and y, they basically take values from plus and minus 1. So what we can do is basically extend this domain. So we will have values not only plus and minus 1, but a larger domain. And what we'll have on the left side is that these unit vectors will not just be any unit vectors on this high dimensional unit sphere. We will also have some constraints about the angles between these vectors. Okay. So this is the results. And the techniques that we use is the following. So the first thing to do is we suggest a semi-definite relaxation, a natural semi-definite relaxation for max score. And then we show how we can extend Crevin's rounding method to allow more than 2 clusters in the output. And we also show how we can adapt this relaxation and rounding technique for the problem of max k-core. Okay, so does anyone have any question till now? Before we're going to talk about the algorithm or the relaxation. Okay, so if you asked me until now, this is a good place to listen again. Okay, so this is our relaxation for the max score problem. So it's a very simple relaxation. And basically what we have here is a vector for every node in the graph. So for every node V, we assigned a unit vector, and we also demand that this, so we assign a vector and we demand that this will be a unit vector. And in addition, we want that for every 2 nodes in the graph, the inner product between YU and YV will be at least 0. So basically what this means is that all the vectors lies in the same orthant. And orthant is just a fancy name for high dimensional quadrant. Okay, and what is the objective? We have this objective, and you can see that if two vectors are the same, that is, if they are in the same cluster, then the inner product is 1. And if you plug it in here, then you get +1 for a plus edge, or -1 for a minus edge. And if two vectors are far from each other, that means that they are orthogonal. Then if the inner product is 0, and if you plug it in here, then you get -1 for plus edge, or +1 for minus edge. So this semi-definite program is indeed a relaxation for our problem. And you can see that this relaxation is also good for general graphs, not just bipartite graphs, but we're going to round it for bipartite graphs. Okay, so let's see the algorithm. The algorithm is going to be quite simple. Okay, so we start with the bipartite graph. You can see that we have two sides, and the edges are either have a plus sign or a minus sign. And the first thing that we do is we solve this semi-definite relaxation. And we get a fractional solution, which is basically a set of vectors, y1 to yn. And they all lie on this high-dimensional unit sphere. And you can see that they are all in the same orthant. Okay, and then what we're going to do is something a little bit different. And we're going to transform these vectors. So we're going to apply transformation. And now you can see in this low budget animation that the vectors shifted a little bit. They are no longer in the same orthant. They can be farther from each other. And okay, so now we have this new set of transformed vectors. And now we just want to somehow cluster them into clusters. So if you think about it, what is the most natural thing to do if you want to cut a ball into two halves? So you can just take a knife and cut it through the middle. And this is exactly what we're going to do. We're going to take a random hyperplane that goes through the origin, and it will split this sphere into two parts, into two hemispheres. So we're going to draw a random unit vector or random hyperplane that will go through the origin, and it will split this hypersphere into two pieces. So you can see now we have this upper part with the green vectors, and this lower part, this lower half sphere with the red vectors. All right, so now we have two clusters. And I can tell you right now that we can stop here and just output this solution, but the approximation factor will not be good enough. So what do? We want to cluster it one more time. And how we're going to do it? We're going to do it in the following way. So we choose one of the two clusters at random. Let's say we chose this green cluster. And we're going to draw another random hyperplane. And we're going to split only this green cluster with this hyperplane. So let's say, again, that we chose this green cluster. And now we have this blue hyperplane. And now we have two clusters. We have the green clusters and here the blue or purple cluster. And we didn't partition these red vectors. We only partitioned this green cluster, the green vectors. Okay, so now we have three clusters. We have the red vectors, the green vectors, and the blue vectors. And this is going to be the solution. We're going to have only three clusters in the solution. So this is the output of the algorithm. Okay, so it's a very simple algorithm.
You had 4 clusters, then you would split the greens, and then you would split separately the reds.
Okay, so this is a good question, whether we want more clusters or not. And we'll talk about it in a few minutes. Okay, so here in this algorithm, we have only 3 clusters. Okay, so I think that the only main...
I have a question, but where did we use the fact that it's a bipirate graph? I mean,
okay,
why did we need that?
It's another good question. The only point that we use this fact is in the third stage in the algorithm, in the transformation of the vectors. So this is going to be the main issue in the analysis of the algorithm. Okay, so let's go to the analysis. So indeed, we want to use the fact that the graph is a bipartite graph and achieve this good approximation factor. So how are we going to analyze this algorithm? We're going to analyze in an edgewise manner. So we denote the contribution of the edge UV with the random variable XUV. So again, you can see that XUV will be either plus WUV or minus WUV. WUV is the weight of the edge UV. And then we can denote the contribution of this edge to the semi-definite relaxation by this number, ZUV. And if we can show that there is some constant C, such that for every edge UV, this number, the expected contribution to the solution over the contribution to the semi-definite relaxation is at least C, then we get a C approximation for the problem. But this way it will not be so easy because there is a problem here that the signs of this value are, they can be negative. So if, for example, this is positive and this is negative, then you can show that this will be at least some positive constant C, right? So what we're going to do, we're going to do something a little bit different. And we're going to show that, okay, so we're going to transform the vectors YU to a new set of vectors, Y tilde U, and then we want them to satisfy that the expected contribution of the edge, every edge in the graph, will be equal to exactly C times the contribution to the semi-definite relaxation. And then we will get a C approximation for the problem. Okay, so again, because these numbers can have different signs, they can have negative sign. We want to transform the vectors in a way that this will hold for every edge in the graph. Okay, so before I show you the transformation, I want to talk a little bit on this value, the expected contribution of the edge UV. So let's first try to calculate this number. Okay, so I want to calculate this value. So I'm going to start with a very simple fact, and it is that if you take two unit vectors, X and Y, and a random unit vector Z that is chosen uniformly on this n-dimensional hypersphere, then what you get is that the probability that these two vectors, X and Y, will be separated by the hyperplane that the vector Z defines will be equal exactly to the angle between xy, theta xy, divided by pi. Okay, and you can see that, for example, if x and y are the same vector, then they will be separated with probability 0. And indeed, you cannot separate them with an hyperplane. And if they are opposite from each other, then you will always separate between them. And indeed, the angle between them will be pi. So this will happen with probability 1. So it's very easy to prove this fact. You can basically look at the vector on 2 dimensions. Okay. Now, when we have this fact, we can use it to calculate what is the expected contribution of every edge. So if you look at the algorithm, what we did is you take one random hyperplane, and then you choose one of the cluster at random, and you split it with another random hyperplane. So you can calculate the probability that 2 nodes will be in different clusters, and then you can get the expected contribution, and it will be this value. So the expected contribution of the edge UV will be equal to this expression if U and V is a plus edge, or just the minus of this expression if it is a minus edge. Okay. And again, here, theta UV is the angle between the new vectors, the YU and YV, after the transformation. Okay, so we have an expression for the expected contribution. So now I will remind you that the contribution of every edge to the SDP solution is exactly this value. So this is what we had in the objective of the semi-definite relaxation. So for plus edge, we had this value, and for a minus edge, we had this value. So if you take this value and you compare it with this value, then you get this very simple, or not so simple, equation, which is the following. So here we basically have the contribution to the solution, and it will be equal to C times the contribution to the semi-definite relaxation. Okay, so if this will hold for every edge in the graph, then we get a C approximation. So we want to somehow transform the vectors in a way that this will hold for every edge. Okay, so I think there's a little mistake. Here the angles should be theta tilde, I mean, after the transformation. Okay, so what we can do is to solve this equation, right? We can solve it for theta. This is a quadratic equation, and we get two solutions. So one of the solutions will just be irrelevant, and we get this solution, get this null equation. And what we're going to do is define the following function. We say that f of x will be equal to the cosine of this value, and we replace the inner product between yu and yv with x. Okay, so we just define this function. And you can see that if you apply this function on the inputs of the matrix, sorry, this is the thing. Okay, so if we apply f on the matrix A, where this matrix A is the matrix of the inner product between vectors in the original solution, then you get the required solution. But we still want to show that the new matrix will be a PSD matrix. It is a positive semi-definite matrix. So you can decompose it and get the new set of vectors. And we also want to show that we have ones on the diagonal of the new matrix. That is, that the transformed vectors will still be unit vectors. So these two requirements are crucial for the algorithm. So the function f will not be enough. We cannot just apply it on every entry in the matrix. We need another function, and the function is going to be this function. So we're going to define g of x to be this sum. And what is the sum? We have here fk, or the absolute value of fk, where fk is the coefficient of xk in the Taylor expansion of f. Again, f is this function, and we define the following function g of x with respect to f. Okay. So now we have this function f of x, and we have g of x, and we are going to define the following transformation. We say that in the new matrix, A of ij will be equal to f of aij. Again, aij is just the inner product between yi and yj. And we apply f if I and j are in different sides of V. They are in different sides of the bipartite graph. And if they are not in different sides, then we're just going to apply g. G is this function. Okay, and this is the only point in the algorithm that we use the fact that the graph is a bipartite graph. All right, so now we want to show that this new matrix is a positive semi-definite matrix. So how are we going to do it? We are going to define a set of vectors that their inner products will be equal to the entries in the matrix. Okay, so before we're going to do that, we're going to define the following numbers. We're going to say that AK is equal to the square root of the absolute value of FK, and BK is equal to the sine of FK times the square root of the absolute value of FK, right? So the A's are just the square root of fk without the signs, and bk is like ak, but with the original signs of the coefficients in f. So now we are going to define this set of vectors, this y prime. And now it will be based on the bipartite structure of the graph. So if u is in v1, in the one side of the graph, then we define the following vector. We have y prime u, which is the following vector. We have a0, and then we have a1 times yu, and here yu is in fact a vector. So here we have n coordinates in the vector. And then we have a2 times the tensor product between yu and itself. So here we have n squared coordinates in this vector. So in fact, we define a vector of infinite length. And if u is in v2, then we define this vector, but instead of a's, we have the b's value. Okay. So again, this k times tensor product for yu with itself is in fact n to the power of k coordinates in these new vectors. So now we're going to look at the inner product between this set of vectors, and we're going to show that they will be equal exactly to the entries in the new matrix. So before we're going to do that, there's a very simple and useful fact about this tensor product. And it says that if you take two vectors, u and v, and you look at the inner product between this vector, which is the k times vector tensor product of u with itself, and this vector, which is the k times tensor product of v with itself, then the inner product between these two will be equal exactly to the inner product between u and v to the k. And this is true for every two vectors, u and v, and integer k. Okay, so now let's show that the new vectors are good. So if they are both in the same side of v, that is, if the two nodes u and v are in the same side in the bipartite graph, then what we have is that the inner product between yu prime and yv prime will be equal exactly to this sum. And here we have ak times bk times the inner product between these two tensor products. And we know from the definition of ak and bk that if we multiply them, we get exactly fk, because ak is the square root of the absolute value of fk, and bk is, again, the square root of the absolute value of fk times the sine of fk. So what you get is exactly fk. And here, you can just use this fact, and you can say that this product is exactly the inner product between yu and yv to the power of k. And now, if you look at this sum, this is exactly the function f evaluated at yu, that yv, because fk are the coefficient of the Taylor expansion of f. So this is exactly f of yu. All right. So this is the case that u and v are in different sides of the graph. And the other case is that they are in the same side. So we can assume that they are both in a v1. And what we get is the following sum. Now we have ak squared, which is exactly the absolute value of fk. And again, this inner product is exactly equal to this. And now if you look at this sum, what you get is exactly the function g. This is how we define g. Okay, so in either case, what you get is that the inner product between these new vectors is exactly the entry in the matrix A. So what you get is that this new matrix is a PSD matrix. So you can use the Cholesky decomposition and get this new set of vectors. Okay, and another thing to notice is that in the analysis of the algorithm, we only care for the edges in the graph. We don't care for nodes that are in the same side of the bipartite graph, because we know for sure that they are not connected with an edge. So we don't care that we change that, that inner product between them.
But don't you want one on the diagonal?
Yes, that's exactly what we're trying to talk in the next slide. So now we only have to show that the new vectors are still unit vectors, right? Because this is what we assume in the algorithm. And so we just want to show that this vectors yu prime is a unit vector. So let's see. Indeed, this inner product of yu with itself will be equal to this sum. And this is exactly G evaluated at yu.yu. But we know that the original set of vectors are a unit vector. So yu is a unit vector, and this will be equal exactly to G of 1. Okay, so what is G of 1? We can show, which is quite technical, but we can show that the function G of x is exactly this function, f of minus x minus this, this part. Again, f0, f1, f2 are the coefficient of f, the coefficient of the Taylor expansion of f. Okay, so you can just plug 1 in this expression, and you get G of 1, and you get an expression that depends only on the value of C. So if you let C to be the solution to the equation G of 1 equal 1, then we're done. And then you get the approximation factor to be exactly the value of C. So it turns out to be roughly 0.254, and this will be the approximation factor of the algorithm. Okay, so this completes the proof of the algorithm. Okay, so if you don't have any question, I will just talk a little bit on a way to improve this algorithm. And if you think of what we did with 3 cluster algorithm, it's just like choosing 2 clusters with probability half or 4 clusters with probability half. So you have to prove it that this will be the same. But now you can ask, maybe we can choose 2 clusters with probability p and 4 clusters with probability 1 minus p, and then try to find the optimal p that will give you the best approximation. And it turns out that if you choose p to be equal roughly to 0.49, then you get a 0.2551 approximation, which is slightly better than the 0.254. And you can see that this is very close to the 3 clusters algorithm. You only choose the probability 0.49, so it's very close to half. And then you can ask, maybe if you can have more clusters, maybe you can have 5 or 6 or 7 and so on, if this will be good. If this will be beneficial for the approximation factor. And the answer is not clear, but is probably no, not with this technique.
So this is all for max-core or for max-k-core?
So this algorithm is good for max-core. And you can also extend it, and this is going to be in the next slide, to max-k-core. So you can define a similar relaxation for max-k-core, and then the relaxation will depend on the value of k. And you can have similar algorithm to round this, this relaxation. Okay, and that's it. This is the end. So if you have any questions.
Okay, so let's thank the speaker. Any questions?
Yeah, I have a question. Is there any hope of generalizing this to general graphs, not just bipartite?
Yes, it's a good question. I mean, we thought about it, and there is some hardness, but I was not convinced with the hardness. So we thought maybe we can generalize it to general graphs or even complete unweighted graphs. But we couldn't show anything interesting.
Can you explain the connection to Krivin's work?
Yeah, so the rounding technique is similar to Krivin's algorithm. So the idea of transforming the vectors and then building this new set of vectors is very similar to Krivin's algorithm. But what we showed is how you can have more clusters, right? We have 3 clusters. You can have more than 3. You can have any number of clusters and use the same techniques that that he had in this algorithm.
So in particular, this function g and this constant that you get by equating g of 1 equals 1, this is taken from Krivin?
It's not exactly taken from Krivin. It's similar to his proof. It's similar to his technique, right? The idea of building this set of vectors.
No, but this idea of taking the Taylor expansion and taking absolute values, is this in Krivin's work, or is this?
Yes, yes, this is the idea in Krivin's work. Yeah, it's a brilliant idea, yeah. Okay, so if there are any more questions.
Okay, so let's thank the speaker again.
Okay, thank you. Thank you, everyone.
Thanks.